Hello and welcome to Chapter 29, which deals with some of the properties of light waves. Now that we've established that light acts as a wave with the electric and magnetic fields pushing each other forward, we are going to talk about some of the properties that come across because of this. I'm going to start out with something called Huygens principle, which is that every point of a wavefront may be considered the source of a secondary wavelets that spread out in all directions with the speed equal to the speed of propagation of the waves. So basically, what happens is that at any point, a wave will go out in a radial direction, in a direction like a circle or a sphere, which you will see if you drop a rock in a pond, the way that comes out of it will be radial. But if you have all these waves adding up, generally what they tend to do is form plane waves at long distances, which are waves that look like straight lines rather than the radial circular lines. So if you look at the diagram, you'll see that there are plane waves coming into three different slits of different widths. And these plane waves, when they interact with the slits, at the edges, they're going to appear more spherical or more round or more circular, rather, for a two-dimensional space. Whereas the parts of the plane wave near the middle are going to still appear like a plane wave and still appear rather straight. So as the wave gets smaller, or as the slit gets smaller, the wave becomes more spherical instead of looking kind of like a plane wave with spherical edges. Defining this, we have something called diffraction, where diffraction is the bending of light as it passes the edge of an object, creating a fuzzy edge. It also occurs when a wave passes through an aperture. The diffraction of plane waves, shown in figure 29.7, occurs for all kinds of waves, including light waves. Diffraction is not so nice for viewing very small objects with a microscope. If the size of an object is about the same as the wavelength of light, diffraction blurs the image. If the object is smaller than the wavelength of light, no structure can be seen. The entire image is lost to diffraction. No amount of magnification or perfection of microscope design can overcome this fundamental diffraction limit. To minimize this problem, microscopists can illuminate tiny objects with electron beams rather than light. Relative to light waves, electron beams have extremely short wavelengths, which we'll get to in a couple of chapters. Electron microscopes take advantage of the fact that all matter has wave properties. A beam of electrons has wavelengths shorter than those of visible light. In an electron microscope, electric and magnetic fields rather than optical lenses are used to focus and magnify images. As you can see, this is demonstrated in the diagram here, where if you have a large object with large wavelengths, you're going to see diffraction around the edges, as in figure A, whereas if you have a small object around large wavelengths, you're going to see less diffraction, as in figure B. But if you use small wavelengths, then you're going to see basically so much diffraction that the wavelengths are basically cut off by this relatively small object compared to figure A, as in figure C. So the reason that we use long wavelength radio waves when we're talking about when we're trying to communicate information over the airwaves over like FM and AM radio is because you want these waves to not be interrupted too much by going around a building or over a car or something else that's relatively small compared to the size of the wavelengths. You want the waves to be visible after or to be recognizable after they go through a solid object and or go around a solid object and not have that much diffraction as you would see in with smaller wavelengths in point C. Another property of diffraction is Young's double slit experiment, where Young passed waves of light through two slits some distance away and saw that because there was a difference in distance traveled from the two slits, from the wavelets from the two slits, what you would end up seeing if you put a screen up some distance away was that there would be bright and dark spots depending on the interference from the wavelengths uh, some distance away. So if the distance was set so that the wavelength of light or the wavelength of the monochromatic light that was going through was going to interfere positively, was going to have positive interference, then you would have a bright area. But if you have negative interference, then you have a dark area. And when you look at this creates something called a diffraction pattern, as you can see on the bottom left-hand side, where you have alternating bright and dark areas depending on the interference of the wavelets from the two slits. Another way you can see this interference is with thin films, where a thin film is something that is about the wavelength of light or relatively close to the wavelength of light, some integer number that isn't very, very large, where if you take air and then put gasoline over a puddle of water, what you tend to see the light at certain wavelengths is going to bounce off the top of the gasoline, and then there's going to be a bounce of light that passes initially through the gasoline but reflects back from the water. And these two wavelengths are going to, or these two instant lights, if they are in phase with each other, if they're the same color and in phase, which means that they have constructive interference or positive interference, then they're going to end up having uh, positive interference, which means that you're going to see that color in particular. You're going to see that color interfering positively and being brighter than other colors that don't have positive interference. But as you can see from different angles and different thicknesses of the gasoline, then you are going to get different colors interfering and shining at different spots on the gasoline. So if you look at a thin film of gasoline over a water puddle, you'll see that it's very colorful. It's like reds and greens and blues all mixed together, all in different spots. But depending on the thickness of the gasoline layer and depending on the angle that you're looking at it, these different colors are going to interfere constructively as you see them, and this is going to cause you to see these bright colors rather than just like the white light that is shining down on the gasoline. Another thing I want to talk about is polarization, where initially, if you have a lot of light coming out of a flashlight or something, the overall polarization of the flashlight is going to be no polarization. So it's going to go, the electric field can oscillate up and down, or it can oscillate side to side, or it can oscillate in some combination of these two. However, if you pass it through what's called a polarizer, then it's going to do something like you see in figure A, where only light that is vibrating up and down, that is going up and down, or is going to fit through the slits of your polarizer, and it's going to knock out any vibration that is not going up and down, as you can see in figure A. So if you took a rope and started moving it up and down, and passed it through a fence, the only way to get through the fence is if it's going through up and down. Any combination, anything going side to side or off at an angle is not going to go through the fence. You can then set it up so that a polarized light is not able to go through a second polarizer, which is perpendicular to the first polarizer. So if it's at some angle, then some of the light is going to get through. But if it's at a 90-degree angle, then all the light that is polarized to go up and down cannot go side to side. It's going to be perpendicular to that, so none of the wave is going to be transmitted through the second polarizer. You can see this in this setup where you have two polarizers. In the first picture, both of the polarizers are at the same angle, so all of the light that goes through one polarizer goes through the second polarizer. But this is only going to be about half of the light that you would see if you had no polarizers. However, if they're at a 90-degree angle, then none of the light going through the first polarizer is going to go through the second polarizer. That is, as we saw with the fences, just something that's happening because they're perpendicular to each other. This is also the case in polarized sunglasses, where light that's reflecting off of shiny things such as water or glass tends to be horizontally polarized. I don't remember exactly why this is, but it is the case, meaning that the light is vibrating, the electric field is vibrating back and forth in the horizontal direction, side to side rather than up or down. So what you have is a polarized sunglass which has a polarizer which is going up and down rather than side to side and is knocking out all of the glare that you would get from the ocean waves. What is interesting to note is that if you introduce a third polarizer, which is at some angle in between the two polarizers that are perpendicular to each other, then what will actually happen is that some of the light that goes through the first polarizer, through the vertical polarizer, is going to go through the second polarizer and it's going to be polarized at an angle. It's going to be polarized at, in this case, about a 45-degree angle instead of vertically. And then because 45 degrees is not perpendicular to the horizontal polarizer, it's going to go through the horizontal polarizer, and you can see some of the light passing through, even though you are still having those two perpendicular polarizers. This is really interesting if you think about it from a measurement perspective, where light is first measured to be polarized along the vertical axis and then is measured to be polarized along that 45-degree angle axis, and then finally is measured to be polarized along a horizontal axis. So what this means is that you have two measurements, the vertical and the horizontal measurement, which are completely incompatible with each other, but because you added a third step where it is measured to be somewhere in between the two, you are able to see the light passing through